So at that time, I was thinking that whether during pregnancy, maybe the baby would release some cells into the blood of the mother. And then I actually started a project doing that in the 1989. But the problem is that even though we were able to show there are some fetal cells which enter maternal blood, but the concentration is extremely low. So I actually spent 8 years on this project without a lot of success. So and then, by the time of 1997, I decided it's probably about time to go back to Hong Kong, because that year, of the return back to China, a lot of jobs were available in Hong Kong. So I applied and got into Chinese University of Hong Kong. And then there was a period of about 3 months when I have resigned and waiting to come back, nothing to do. And I know that when I go back to Hong Kong, I need to start a new project, to start a new career. And interestingly, just about 3 months before I came back to Hong Kong, I saw in this issue of Nature Medicine that there are 2 papers which says that tumors will release its DNA into the bloodstream of cancer patients. And then suddenly I have a strange thought, because I thought that a baby living inside mother is a little bit like a cancer growing in a pregnant woman. And also in my medical training, I've never seen a cancer which is as big as an 8-pound fetus. So I was quietly optimistic that there should be some fetal DNA in the plasma of the mother. But the problem is, how do you actually detect this DNA? Because I was working on cells. Up to that point, I have no idea how to work on cell-free DNA. But interesting, as you know, and also I don't know how do you prove this phenomenon exists, okay? And then after thinking a while, I thought that the easiest way to show it exists is a situation of a mother carrying a baby boy. If our thinking is correct, then the baby boy should release the male chromosome into the blood of the mother. But then the question, how do you get this DNA out? And at that time, I wasn't very well funded, right? Because I just came out with my PhD in 94, and I want to come back in 97. And of course, for those of you who have been to the UK, you know the food is not exactly good in the UK, right? So, and then I spent a lot of time actually cooking instant noodles in my room. And of course, and I thought, well, how about the cheapest way is to cook the plasma like you cook instant noodles. So just kick some plasma and just boil that for 5 minutes and then see what happens. And interestingly, when I actually use those boiled soup, 100 microliter of that, and take it for PCR, for the Y chromosome, I was able to actually get a signal in some pregnant women and no signal in others. And later on, when I followed those women, I find that this group all have baby boys, and that group all have baby girls. So this is actually the first demonstration of presence of fetal DNA in maternal plasma. It actually only took me about 3 days to do this experiment. I could not believe my eyes when I first saw it, because I could not believe that the thing which I've been searching for 8 years was actually in the plasma, but not in the cells. And then later on, when we measure the concentration of this fetal DNA, we can find that actually it's present as early as 7 weeks of pregnancy. And then the concentration keep on climbing, probably because the baby is getting bigger. And now I thought, well, what proportion of plasma would be from fetal DNA? Well, I imagine the baby is so small, the mother is so big. Even if I can detect it, we might be talking about 1 in 10,000 or whatever. So I was very surprised when we did the experiment. We find that a mean of some 3 to 6% of all the maternal plasma DNA is from the fetus. And this is really very surprising. And another thing I was wondering is what happened to the fetal DNA after delivery of the baby. Because I was very worried that the fetal DNA might persist from one pregnancy onto another, and that will give you a false positive result. So we recruited a number of pregnant women at the time of cesarean section, and then we take blood serially. And you can see that actually by 2 hours after delivery, the fetal DNA actually has gone completely in most pregnant women. So the fetal DNA do not persist. The fetal DNA you detect is that from the current baby. So now, with this newly discovered source of fetal DNA you can get non-invasively, we can do a variety of testing. Now, for example, you can tell the sex of a baby, which is important because some genetic diseases are sex-linked, like hemophilia and some muscular dystrophy, because the mutant gene is on the X chromosome, and men only have one X chromosome, so we have no backup. So those diseases are more likely to affect boys. And we can also use it to tell what blood group type the baby has got, because sometimes if the mother and baby doesn't have the same blood group type, they could cause immunological problems. So those 2 tests are now actually in use in many parts of the world, and accuracy is generally over 99.5%. But of course, the number one reason why pregnant women go for prenatal testing is because they're worried the baby might be suffering from Down syndrome. So a normal individual, we normally have 23 pairs of chromosomes. And the chromosomes are numbered from 1 to 22 in the X and Y. And the 1 is the longest, 2 is smaller, etc. So 21, 22 are the very small chromosomes. And for people with Down syndrome, instead of having just one pair of chromosome 21, they have 3. So the question is, can we detect this extra dosage of chromosome 21 in the mother's blood? And this is pretty tough because sexing, you're telling the whole chromosome Y is there. And blood group, you're talking about different blood group. And here is a quantitative diagnosis. So it actually took us about 10 years to try to address this problem. And it's really difficult because, as I told you just now, 95% of DNA in mother's plasma is from mother, and only 5% is from fetus. So you can imagine the background from mother is going to interfere with this counting. So by the time it comes to 2007, we decided to actually go back to the drawing board and try to construct a system from first principle. So what we're talking about is this. So every mil of the mother's plasma, there's on average the DNA from 1,000 cells. And let's say 95% of this is from mother and 5% is from baby. So it means that every mil of mother's plasma, there are 950 maternal genomes, DNA, and 50 fetal genomes. As I told you just now, every normal genome will have 2 chromosome 21. So you have a 950 maternal ones, then you'll have 1,900 chromosome 21. Now in the fetal side, if the baby is normal, then every fetal genome, there will be 2 chromosome 21. So if it's 50, it will be 100 chromosome 21. But if the baby has Down syndrome, then this will be increased to 150. So now imagine if you can develop a test, will tell you how many chromosome 21 there is per mil of mother's plasma. In a normal situation, it's 1,900 plus 100, which is 2,000. In the abnormal situation, it's 1,900 plus 150, which is 2050. So in other words, if you can develop a molecular test which can tell 2,000 from 2050, then you solve the problem. But of course, for those of you who are physicists or engineers in the audience, you say, well, this is easy, right? You can tell that difference. But if for those of you who are biologists, you know this is tough. Because most people detect DNA by a process called PCR, polymerase chain reaction, which is a type of molecular photocopying. You copy from 1 molecule to 2 molecules to 4 molecules. So it's always a doubling change that you can detect, and not this sort of change, 2,000 from 2050.